Thank you. Yes, so do not wait until the night before, please. I hope you guys are all on top of this. I hope you're working through it. Everything's good. It is due this coming Thursday, the 21st, before class time. So make sure to get it in. Again, you're going to be exporting a PDF and submitting it via Gradescope. Sort of a breaking news on the homework. Originally, the homework was supposed to be due next Thursday as well. Originally, we had sort of intended to give you guys a week to turn that around, but we figured with the project due the same day, that was not a great look for anybody. So instead, it's going to be due the following Tuesday the 26th. So give you a little bit more breathing room, hopefully some time to kind of wrap up the project first. And it'll also give us TAs some more time next discussion section to really focus in on the homework. I think I kind of felt bad we weren't really covering all the material from the homework this week. So I wanted to at least have a discussion section to go through that with you. So doesn't mean you shouldn't start it, but at least you have a little bit more breathing room. So be aware of that. Okay, now before we dive into the material, the moment you have all been waiting for, it is time, very important time. I told you guys this was coming, Zoom background contest. So here are the rules for this. If you wish to participate for fame and glory and a Starbucks gift card, you got to the rules are simple. Turn on your webcam, and then in the chat, you got to paste your name and your background description. Okay, so I got that example there. So for me, and then I'm not doing it, but if I were doing it, something like the Millennium Falcon cockpit, for instance. Okay, then to vote, all of y'all just in the chat, just paste your own kind of thing, and we'll do that. Now I do need a volunteer from the crowd. So somebody who's not participating who can help me count up the votes. And I'm going to stop sharing my screen so that you guys can actually, so that we can kind of go full screen with these. You all can kind of take a look at these. Okay. So who can I get somebody who's going to help me count this? Anybody?
I can go ahead and count if no one else is.
Gabriella, okay, thank you. Okay, so Gabriella, you are official thing. Okay, so let's look at some of these submissions. I'm really looking forward to these. Oh man. Okay. Josh coming in strong with Professor. It's a bold move. Okay. Jake with the depth of Bolter. I'm loving it. Who's rocking the Joe Exotic? Joshua. Nice call. Okay. All right. Sriniketh. Cold Steel the Hedgehog. All right. Whoa, Belle, there's a lot going on there with yours. There's a lot. I feel like I need to just put you on full screen just so I can see everything that's going on with your background. Okay. See, I got a sleepy cat. Always a solid choice. Okay. Sumya. Oh, okay. Tech guys as companies. This is good. Okay. You're making me read for this. Man. I feel like Apple would be a bit more high maintenance as a guy. You know, like they would have better, they would definitely like take better grooming than you would. But okay, let's see. Tyler, I'm seeing, is there Tyler, is mayonnaise an instrument? Okay, cool. Oh man, Anna coming in hard with cats. You're going to give me some awful repressed imagery of that. The trailer alone was just doing it for me. Wait, Jody, is that what I think it is? Is that? Oh my God. It's what's the name of it? Falling, the K-drama. Falling in love with, Falling on You or something? Crash Landing on You. Thank you. Oh my God, it's so good. My wife and I watched that last year. We were so obsessed with it. Oh, it's so good. Oh, good call. Okay, man, so many good entries. Okay, are people voting? So guys, again, in order to vote, you have to copy and paste the person's submission. So let's see, did I miss anybody else? Oh man, some of these are so good. Wow. Okay. So Erica, what's yours? I'm seeing a happy birthday with a little kid.
Yeah, it's
Guppy. Oh,
it's from my
okay.
Carly.
Okay.
Guppy, yeah. It's Gibby's little brother.
Nice. Okay. I never got into iCarly, but I can definitely feel that. Okay. And then Michelle, what are you rocking there? That looks kind of cool. Is that an original drawing? Okay. All right. Nicely done, guys. First time at Disneyland. Oh, that's awesome. That's a cool memory. It's so sad. I heard they're turning Disneyland into a vaccine center like that. Isn't that like the most 2021 thing you could ever hear? Disneyland's now doing vaccines.
Aren't they the ones that let people in like prematurely too?
Yep. Because big business would never put public health before profits, would they? Okay. All right. I'll give people another few minutes, another few seconds to tabulate their votes and their scores, and then maybe Gabriella, maybe at the end of discussion, we'll announce the winners. Okay, cool. Actually, it's just winner. So first place winner, one winner. Let me see. You know what? Sorry, I'm going to take a quick screenshot of this because this is awesome. You guys are awesome. Boom. Okay. We have recorded this for all posterity. All right. To business. Rumor has it we actually got to get some work done in this class. Okay, why did Zoom boot my second computer off? That's not cool. All right, whatever. I'll just share on this computer, I guess. So, well, I'm figuring that out. Okay, and then let me present this. Okay, so kind of a quick, well, now my Zoom is acting up so I can't see, but just a kind of a brief check-in with you guys. How is it coming so far in terms of like the course material, in terms of project one? How is that for you all? Are you finding it okay? Are you struggling at all with it?
I was kind of wondering, like, is there, I know we have like a few different textbooks in the syllabus and there's some like online stuff as well. Is there plans to like, I don't know, like describe which of those books or like which sections or whatever we could go and read up on the material?
That's a good question. I don't think we have a mapping between like books and things. Like I don't think the professor is assigning materials. I don't think you will be expected to read chapters, you know, for like the exams and stuff. It's a good request. Unfortunately, I don't think we have that mapping up there. And part of the reason for that is the professor's kind of like partially updating the syllabus and the material. Lucky you guys, there's sort of more of an emphasis this time on like some statistics and some more stuff than maybe there had been previously. But yes, as a result, I don't think we necessarily have particularly good sort of reading resources for you.
Okay, I was just curious, like, as to, you know, what the quizzes and the final would be. Wait, do we have a final?
Oh, Jesus. Sorry, I was trying to get, Jesus. Okay, that'll be better, I guess. Just trying to pull up the chat because unfortunately I usually have two computers running and that's not working. So if you guys are hitting up the chat, I need to make sure I'm not missing anything. Okay, I think I'm all set. So one thing that I hope you guys are kind of recognizing at this point is that data science is less of sort of an exact science, maybe than you may have sort of been led to believe going in. It really is sort of a bit more of an art than anything else. And part of what you're going to kind of get to see is that a lot of the choices you make in terms of building your models and everything is highly kind of up to the individual practitioner. And this is a process we're going to sort of begin to explore throughout this course, but everything from, you know, which features in your data set do you keep? If you transform them, how do you transform them? If you, you know, for the model itself, what models you choose to learn, what metrics you choose to use. There isn't always a black and white right answer, wrong answer. There are objectively sort of wrong approaches and better approaches, but there isn't always sort of an objectively right approach to this. And in general, sort of the best that we can kind of hope to sort of give you guys in terms of this is sort of an understanding of the ingredients, understanding the parameters, understanding kind of what tends to work, what tends not to work. And then, you know, but a lot of this is guesswork. And when you're building out your models, you know, you will, more often than not, you will spend a lot of time experimenting with different approaches to preparing your data, different models, different parameters, different inputs. There's just kind of a lot of sort of things that you can tweak. And you know, and again, there's a reason why data science as a field does things like Kaggle, has those contests. And it's precisely the fact that like there isn't really sort of always an objective right or wrong approach to things. And you know, for project one of the things I'll say that I've really loved seeing is that we've gotten like a ton of great questions on the Piazza of people sort of already kind of thinking ahead and starting to think about methodologies and being like, well, hey, you know, why are we only doing one model for this? Like, shouldn't we do a comparative model? Shouldn't we look at different metrics? Like, shouldn't we be doing other things? Like, isn't there a problem that we're augmenting these features and you know, introducing collinearities into our data? Like, isn't that problematic? And you're 100% right with all of that. But the thing to kind of note with this is that our goal for project one was really a lot more humble than that. It was what I describe as baking your first cake. It was, you know, we assume you've never done data science before. We assume this is kind of your first time taking the car around for a test drive. We want you to just get your hands dirty. We want you to kind of see the steps in action. We want you to start playing around with it. And most importantly, we want you to start thinking about it in terms of, again, all of these various factors that go into your model. We don't expect it to be pretty. We don't expect the results to be good. We don't expect anything like that. We just really kind of just want you to get that first experience, because I think it's so much more helpful when we dive into all of these like specific topics when you have that 30,000 foot view and you've taken the time to kind of see how it fits into your broader model. So, you know, if we spend, you know, if we do a deep dive on a topic like one-hot encoding, suddenly it makes sense. Suddenly like you understand it in the context, hopefully, of this. So that's, generally speaking, that's the hope with this. So for today, I wanted to kind of finish our code walkthrough. So if you remember last session, we sort of begun, we'd walk through all the preliminary steps. We looked at augmenting, imputing, everything was like looking relatively good. And then we encountered this monstrosity of a text. And oh my God, what was the TA who did this? Not me, by the way, putting that just absolute nightmare together. So I think we want to spend a significant amount of time just kind of diving into exactly what's happening there and kind of walking through some of the stuff that's associated with it. And to help with that, I put together a sample code. It's called the week 2 sample code. Again, I linked to the folder on my Google Drive. So hopefully you're able to access it. If you're not, let me know. But if you want to kind of follow along with that, please do, and we can kind of walk through it. So today, here's some of the specific stuff I want to kind of walk through for the rest of the session. The first thing, again, I want to kind of spend a bit more time talking about augmenting data. I know we've already talked about it. I want to talk about a bit more. Also spend a bit more time on imputing data. We're going to talk a bit more about data types, how to handle them. We're going to specifically talk about a topic called data scaling, which we haven't really addressed, but it's kind of important for us to do it. We'll spend some time talking about pipelining, and then we'll kind of walk through the rest of the code, including splitting your data, learning your model, and then generating and interpreting results. So the first thing to note with data augmentation is that you can sort of augment both rows and columns. And let me throw this out there. Can you think of an example that we've already covered in that the professor's already covered in lecture of augmenting rows? So, and when I say augmenting rows, what exactly, what does that mean in like a plain, in sort of a regular sort of vernacular, I guess? What does it mean to augment a row?
Is it just that you're modifying the data for a specific, well, like a row is like a specific sample?
Yeah, perfect. Exactly right. You're essentially adding data to your data set. Exactly right. You're adding more examples, you're adding more samples to your data. Exactly right. So to add rows to your data is effectively to add more sampling size to it. Okay. So in that spirit, have we talked about anything that could sort of fit into that notion?
I think with the regression, when she multiplied x1 by x2.
Mm-hmm. Okay, good. So that was kind of, so we talked sort of about a few things around there. So things like bootstrapping, things like taking sort of the medium, essentially you're trying to fill in those gaps, right? You're trying to kind of flesh out your data set, add additional sort of context to it. So exactly right. A lot of the models that she's talking about with there are examples of row augmentation. Some other sort of examples of this, and I have sort of an easy graphic here, but this is sort of a common one with computer vision data sets. So, you want a computer to learn 3. Well, obviously 3 occurs in nature that way, but it can also occur in any number of orientations and views. And so oftentimes what you'll do is you'll sort of manually do those transformations and then feed those into your learning model. In a similar vein, time series. You may be sampling data over certain intervals, and you may want to kind of, if there's gaps in those intervals, you may want to kind of flesh them out. And so those are sort of examples of, and so you may want to do like statistical means or things like that to try and like fill in those data, sort of create a more continuous, less discretized data set for that. So those are examples of how you might sort of supplement your data and kind of add additional samples to it, create what we call synthetic data. And by the way, there's a whole sort of cottage industry around synthetic data. A lot of things. We use it, for instance, in like healthcare, where we want to create healthcare models, but there are restrictions in terms of leveraging individual patient data and stuff. So if we can generate synthetic data that sort of matches the general parameters of our real data set, but doesn't actually have any personally identifiable information, that's a really kind of useful thing for us to do. So there's a whole industry just around creating synthetic data. So again, just something to kind of have in the back of your mind. Now, for this project, we had you augment columns. And essentially, we asked you to sort of create new features based on the data that you already had on hand. And some of you kind of already flagged this, but it's kind of a little bit problematic, the type of features we had you work with. And does anybody kind of have a sense of what would be problematic? Okay, and just as an aside, are people, okay, oh, sorry, I'm getting some chats there. Okay, so generally speaking, the type of transformations we're asking you guys to do, which is just basic sort of arithmetic, adding columns, dividing columns, those are sort of linear relationships between between features. And generally speaking, learning models are supposed to be able to kind of tease out those relationships already. That data is already theoretically embedded in your existing data. All you're really doing by adding an additional label is introducing collinearities, and you're introducing so you're doing two things. You're introducing data that's already closely correlated with existing data in there. So the entropy, let me pause there. When I say entropy, I need to actually clarify that. Entropy is the notion of sort of, this is kind of an important concept we're going to get into in data science a little bit more. There's the idea of sort of information and noise. And there's this constant balance with this. And in fact, to the point where where if you add too much noise into your data set, you'll get this weird counterintuitive property where your model will actually improve its performance, but it's actually harming the data. And we'll get into that. That's a whole other talk for another day. But the point being that you're sort of adding these data sets that are already collinear, that information is already effectively captured in your existing features. You're not really sort of learning anything new about the data by creating that. All you're doing is adding features that ultimately yield to things like overfitting. So that's not sort of a perfectly good example. And again, I think that's something like when we get into things like principal component analysis and dimensionality reductions, we're going to talk about kind of how and why the dimensionality of your data is so important. But for now, let me just kind of leave it at that to say that the features we asked you to do aren't particularly good or useful in this context. So what are examples of maybe features that are more useful? So I have kind of a few examples here. So the first thing would be things like log transformations. I have sort of an example here. So things that aren't necessarily linear, but there are relationships in the data. And maybe, something like your learning model isn't necessarily going to pick that up. And here's an example of kind of a log transform data. So when you look at sort of the data regularly, there doesn't kind of appear to be, sort of a nice linear relationship. But when you do a logarithmic do a transformation, i.e. something that's not necessarily linear, something that isn't necessarily immediately interpretable in the data, we get this nice, actually very kind of consistent looking trend pattern. So that's an example of that. We may also have, this is another thing that's very, very common, is a feature label mismatch. And an example of this is data collected continuously, but the labels are entered at intervals. And let me give you an example of that. So, we do a lot of times in our lab, we'll do studies where we're going to be collecting data continuously. We may have like an individual may be wearing a sensor, and it may be sort of transmitting data to us at, microsecond or millisecond intervals type deal. And then we're going to ask them to sort of provide some labeling, maybe things like their level of physical activity for the day, things like their emotional state in a given day. And so you have this data that's coming through, again, like almost continuously, and then you have like a label. And you sort of need to ultimately be able to kind of match your data to your labels. And so typically what you have to do there is you have to do some kind of sort of summation or some kind of, of pairing up to sort of align your labels and your data. So in that case, oftentimes what ends up happening is we'll take sort of summary statistics of the data and return those. So, for instance, if we're collecting data on a day-by-day basis, we'll probably return summary level statistics for that day. We may take like mean, median, min, max, standard distribution, things like that, and have those as features that we put into our learning model, not necessarily the raw data. And then the last thing that I'll note is what sort of noted at what we'd call categorical transformations. So these are sort of nonlinear transformations in which they're sort of really kind of critical distinctions. So an example might be, let's say you're looking at latitude and longitudinal information, and then you come to, let's say, the US-Mexican border. Well, suddenly the data that you're collecting immediately north of the border may look very different than the data you're collecting immediately south of the border. And you may be seeing sort of a nice trend line, and then suddenly there's this rather dramatic break. And again, that kind of follows a nonlinear approach. And so for something like that, it's kind of oftentimes important for you to kind of be able to do a sort of a conversion over and create those categorical variables that you can then feed into your model that will say, oh, yes, treat everything north of here as one category, treat everything here as another category. So I wanted to put that into context to say that again, for our purposes, project 1, you're not really generating useful features by augmentation, but in fact, there are a lot of really, really useful transformations that you could do to your data, augmentations you could do to your data that could generate really useful stuff. So let me pause there. Any questions around that? Okay, I have lulled you all to sleep. So imputing is something we spent a lot of time last section, so I don't necessarily want to spend much more time on it now, but I did kind of want to note that, I like this graphic. It's just sort of understanding the difference between like a 0 value and a null value. And, a 0 undefined, null, like the important distinctions. And we talked last time about some strategies you might take. Spoiler alert, if you haven't looked yet, it's actually outright one of your homework questions is going to be about imputing values. So you remember we talked about different things. We talked about potentially like deleting rows that have missing data values. We talked about deleting column features if there are too many. We talked about different strategies for imputing it. Things like assigning an arbitrary value, things like taking some kind of statistical assessment, a mean, a median, whatever, and impute, invert that. So we talked about a lot of different approaches and potentially sort of when we might want to use one or the other. But again, just kind of be aware that that's something that's out there. So, you know what? If you guys can give me just a second, I'm going to try to pull this up as well on here and see if we can get this running on my computer as well, because wouldn't that be lovely? Why is this not letting me share? Okay, good. Okay, yeah, Zoom is just not working on this computer. Okay. All right, so sorry, I'm going to actually have to go and download the data myself. If you guys will give me a second, but let me read to materials. Okay. Download and then drinks of CSV. Download, perfect. open. Downloads. To sample code. Okay. And kernel restart. All right. Let me pull it back up. So hopefully you have this. So I created a really, really dumb. Ooh, that was some weird reverb. Hello? Okay, sorry about that. Okay, so basic data set called drinks.csv. Back in the good old days when we could still go out in Westwood and have stuff. So a handful of random places. We have, if you look at the data set, we have a neighborhood associated with it. We have the type of drink the place is, and then we have an associated price with it. So the first thing I kind of want to look at with this is we'll just like pull an info on this and let's look at the kind of data we're dealing with here. So here we have a total of 4 features: name, neighborhood, type, and price. Of those, so well, let me pause and ask, are any of these features problematic from a learning model perspective? What do you guys think?
We need to convert any object data types into a vector or something readable by a model.
Perfect, right? So right now your linear regression, your classifier doesn't really know what to do with something like Westwood, Santa Monica, Brentwood, alcohol, right? Those are not really meaningful things. And in fact, in general, like we said last time, unless you're dealing with an int or a float, most of the time, the model just doesn't know really how to handle that. So we're going to need to do something to these, and specifically because we know that with name, neighborhood, and type. So the first thing we got to note here is that name. So I'm going to drop name. Generally speaking, that's not really a useful thing. There isn't really anything we can do with that from a learning model. And so now we're left with neighborhood and type. So these are examples of categorical features. So what do you think? Let me see where I am with this. Okay, so let me see here. So what do you guys think we could do here for categorical feature? I should be unmuted. How do we handle categoricals? What do you guys think?
Could we like count the values for each category?
Okay, so we could count the values for each category, maybe do sort of summary counts. So that might be maybe potentially a feature you may want to think about augmenting, but ultimately we want to do something similar, but sort of discrete. Okay, encode as zeros and ones. Okay, cool. So Ben, I'm going to get there. That's going to be our next step. But the first thing, so if you recall, the problem with these right now is that models don't know how to deal with strings. I can't feed a linear regression model to say Barney's Beanery, Rocco, like that's not meaningful for them. What they generally take is some kind of numeric inputs. So the first idea says, why don't we just simply take all the discrete values of these categories and replace them with numeric inputs? Right. So, there's no reason why Westwood has to be Westwood. Why can't Westwood just be a number? And a number is something that we can plug into our data set. Right. So, and that's precisely what we're doing here. So this first sort of line of code here is what's known as a label encoder. And that's precisely what we're doing. We take our feature and we do we call a thing called a fit transform, which is part of your whole pipeline thing. It sort of takes it and feeds that in and then converts it into labels. So now if we look, if our inputs were Westwood, Santa Monica, Brentwood, our outputs are 2, 1, 0. So they've assigned 2 to Westwood, 1 to Santa Monica, and 0 to Brentwood. And we do the same thing for type. Now we have 0 is assigned for alcohol and 1 is assigned for boba. So sounds good, right? I mean, our work here is pretty much done, isn't it? Is there any kind of problem with this? Can anyone think of maybe why this is not necessarily always a perfect solution?
If we have more than 2 categories at least, let's say you like have 0, 1, and 2, that implies that 2 is more similar to 1. If you're like, or 0 is more similar to 1 than 0 is to 2, even though they're discrete variables and there's no real connection like that.
Perfect. Okay. Awesome. I'm so glad you said that, because that's exactly right. So 0 and 1 is fine, not really a problem for us. But when we get into multiple categories, it implies, so you mentioned like associativity relative to, you know, that a number, the proximity of certain values you would assume that there's kind of an association between them. It also indicates a what we call an ordinality, an ordering. So, you know, by rendering our neighborhoods as 0, 1, and 2, we have implied that Westwood is somehow more than Brentwood. And concurrently, we have implied that Santa Monica is more similar to Westwood than Brentwood is. Because when you feed that into your model is going to look at that and it's going to make associations. It's going to assume relative values that are associated with those numbers, right? Those numbers. So we came in with the idea of saying, hey, you know, we can't have a string, so let's just stick a number in there. But the problem is the numbering is arbitrary for the most part, right? We don't really care what number it is. We just needed something that we could fit in there. And by doing it this way, we've effectively created a hierarchy that didn't exist in our data previously. So effectively, we're sort of lying about the data that we're feeding into our model. Does that make sense to everybody? Why that's kind of problematic? Okay, so how do we handle this? What can we deal with this? Spoiler alert, what we covered in lecture, one-hot encoding. So here was the idea of fundamentally of one-hot encoding. What if we can take each unique categorical value? So within, if we have a categorical feature, we take each distinct value and create its own binary column. And then we just simply make it a binary absent or present. So in our example, we take the values of Westwood, Brentwood, Santa Monica. They'll get their own column with present and absent there. And so, for instance, you can see here sort of a sample output thing here, where we take neighborhood and we one-hot encode it. And so this one-dimensional feature here becomes a three-dimensional feature in which this is Brentwood, absent present. This is Santa Monica, absent present, and this is Westwood, absent present. And then that way, we can feed then this into our learning model, because really all we're trying to say is, does a particular row have a particular feature of Westwood? Does a particular model have a particular feature of Santa Monica? Does a particular model have a particular feature of Brentwood? Did you guys kind of see how that works? So, and then let's see, I think the next topic is scaling. So before I jump off this, yeah, okay. So then let me turn around and ask you guys another question. So this one-hot encoding seems like a really good idea. Why wouldn't I universally one-hot encode?
If you had continuous values and you wanted to one-hot encode those, you'd have to have vectors of infinite length. which doesn't make sense.
Okay, good. So yeah. So there's no question if you had a continuous variable, if you had, let's say a float versus an integer, you probably would not want to hot encode that. Yes, because every discrete value that would just that would render the dimensionality of your data so problematic that that it almost wouldn't be worth doing. So that's one potential issue, right? If you have, or even if it isn't necessarily a continuous variable, but even if there's just so many unique inputs that it basically kind of renders it useless. One example might be name, for instance. I could theoretically hot encode the name, but then every discrete value would be its own feature. And what is really the point of doing that? So yeah, so that's a really great example. Okay, so that's definitely something we don't want to hot encode. What else might we not want to hot encode? While I craftily try to eat lunch. Somebody please talk.
If we go back to ordinal values, it's probably better off just to leave it as enumeration. If we're talking about spiciness, we can have mild as 0, spicy as 1, very spicy as 2. And if we leave one hot encoded, our model has to learn it rather than us just giving it directly.
Perfect example. Yes. So, and spiciness is a great example of that. Let me give you another example. What if we have a feature of age? Would it make sense for us to hot encode a person's age and treat every year as a discrete feature? So instinctively, the answer is no, right? Because that ordinality is important. Remember what we had talked about before. We didn't want to create a scenario in which we were introducing associativity and ranking where it didn't exist. But if that does exist, we don't want to break that in our data because that's very useful data. It is useful to us to know that somebody, if we have 3 data points, one person who's 70, one person who's 69, and one person who's 20, the person, all else being equal, the person who is 69 and 70 will generally have much more in common than the person who is 20. And we want to treat that associativity as a feature. We want our learning model to learn that relationship. We don't want it to treat 80 as a discrete feature, 79 as a discrete feature, and 20 as a discrete feature that are completely independent of one another. So I believe it was Tien who said that, where that relationship exists, you don't want to destroy that relationship. You want to pass that relationship on into the model. So whether it's something like degree of spiciness, where 0 to 5 being non-spicy to, oh my God, take me to the hospital now, you do want to capture that relationship. So, so again, sort of an important thing to note here. So that's why I kind of show you label encoding and hot encoding. There's always, if you have categorical features, you may or may not, there's not always a right way to do it. You may want to think strategically about how you do it. I will note that label encoding generally is somewhat arbitrary in terms of how it assigns the labels. It's also relatively easy for you to kind of just write a very easy conditional that just sort of translates, let's say we wanted to assign, for all, if neighborhood equals Brentwood, then neighborhood categorical equals 1, something like that. Like you can write a very simple conditional statement to sort of manually assign numbers to categoricals. But yeah, so that's generally speaking kind of how you want to handle categoricals. Let me see. Can increase the training time if you introduce more twos. Yeah, so exactly right. So Ricky, you're exactly right about, the more features you introduce, introducing more features introduce a whole bunch of problems. And I'm debating how much we want to get into this now, but yeah, long story short, it does increase it generally makes it harder for the model to train, but it also increases the chance of overfitting of your model. And we'll get into precisely why that is, but the more features you introduce, generally, the more likely it is that your model will overfit on those features. So there really is a trade-off in terms of doing that. You don't want to go crazy in terms of adding features. You really kind of have to be a little bit careful about the dimensionality that you introduce to your data. So there's another kind of thing that's happening in the data set, and you may have noticed it. Where is my project one? Is this the right? Yeah, project one blank. So scrolling down to here, you may have noticed that we have this line here, standard scalar, that kind of threw it in there, no context, no anything. That's what I want to talk to you guys about now. So another kind of thing to note about our data set is that different features will have very, very different degrees of magnitude and range. So classic example of this, let's say that I'm talking about, let's say I'm taking demographic data on individuals. So I may have their age, their number of years that they're employed, and then something like their salary. And so we can have a sort of very, very high degree of magnitude in terms of the relative value of that. So something like age will be in decades and whatever. Whereas income may be in the hundreds of thousands, potentially even more. And turns out not, models can also be sensitive to the degree of magnitude of these different features. And so, an easy example of this is something you've already learned is KNN, right? So let me turn that around and throw it to you. So how does KNN work?
So basically sorry about that. Basically you use like the closest points in the data set to determine if it's classification, you would determine which class they belong to. If it's numerical, you might determine, like where in which range they might be for certain
Perfect.
points.
Perfect. Thank you, Rob. So right, so a KNN, it literally, the K nearest neighbors, it just kind of looks at a data point that doesn't have a label. It looks at however many of its nearest neighbors, and it uses those neighbors to either predict a value for it if it's a predictive regression, or if it's a classification to classify that value. So, and imagine if you have, let's say you have a two-dimensional data set, and one dimension is age and the other dimension is income. And so age is, nice in years, let's say from 20 to 100. And then income ranges from, let's say 10,000 to 1,000,000. If you're looking at a K nearest neighbor, how important do you think that x-axis of age is going to be? Right, presumably not that important at all, if important at all, right? Because even the maximal distance along that axis is 100, whereas along your y-axis, where you're dealing with a range of hundreds of thousands, even the smallest distance will be larger than that largest distance in your x-axis. So if you were running a KNN model and you didn't scale your data, it would only look at income. It would not care at all about age, because age has literally no impact in terms of the relative distance of those points. So obviously that's not good, and we need to kind of do something about it, because ultimately that's an example where we're feeding data into our model that implies a degree of importance that doesn't necessarily exist, right? We may want to treat age and income as equal, or at least tell our data to start off with that assumption. But right now we're not doing that. And so how do we fix that? We have to scale it. And that's exactly what this normalization does, that this normalization step does. And so there's sort of a number of ways of doing it. The way that we did in our example data set is what's known as a standard scalar. So standard scalar essentially takes a feature, let's say income, and it assumes it's a normally distributed feature in which the mean for your value is 0, and there's a standard deviation of 1 and -1. So if you imagine your little normal curve with the mean value being 0, and then your standard deviation is at 1 and -1. And you essentially reparameterize all of your data around that scale. So if the average is 50,000 for that thing, that now average is equal to 0. Other methods can be what's known, so there's an example of min-max, which shrinks your entire feature range to a 0 to 1 range. The max value is 1, the min value is 0, and then everything sort of falls in between. And so, you know, there are other sort of examples like that. But that's essentially what scaling your data does. It sort of makes the magnitude of the original feature irrelevant, and sort of treats all features and all data inputs as being equivalent to one another. So again, let me pause at this point. How y'all feeling about that? Okay. Yeah. So okay. So there's a question about whether or not this is necessary for linear regression, and the short answer is it's not. And so this is what kind of this bullet point here is talking about. Some learning models are scale. What do I say? Normalization of features are relevant. Yeah. So linear regression is an example where, because each coefficient is learned, and each coefficient, you know, can be sort of orders of magnitude corresponding to the associated feature, it actually is scale invariant. And so for that reason, theoretically, for a linear regression, you wouldn't have to scale your data. Correct. KNN is an example of where you absolutely have to scale your data. So then there's the question of sort of agnostic, and then there's the question of like, should you ever not scale your data? And that's actually an interesting question. I don't actually know of an example where you shouldn't scale your data. And that's why I would say in general, it's a good practice to do it, because you don't really, I don't think it I don't know of an example of where scaling harms your learning model, but I do know of an example where not scaling it doesn't harm it. So probably you're okay with like a linear regression, whether or not you scale, but something like a KNN, you absolutely have to. So, but yeah, really, really great question in the chat. Okay, question about this. Let's see here, and then I'm going, okay. Okay, so I got a DM coming through. I'll address that maybe when we sort of have a natural break in the class, okay? So let's kind of go back to, where's my week? Okay, so we have this one. So let's take a look a little bit at this code again, so you can kind of take a look at this here. So ultimately, kind of what we've done here is we've begun to sort of concatenate different operations here. And that's really what we're beginning to do here. So we looked at like doing the label encoding step here. Here, we're going to want to do two things to our things. We're going to want to take scale, and we're going to want to take price, and we're going to apply a standard scalar to it. And then we're going to one-hot encode our two categoricals, our neighborhood and our type. And then we sort of combine them together into a single thing called a preprocess. So essentially what we've done here is we've defined this essentially concatenated method that will sort of pull our data set, and then for all of these various features, do these things and then return an output. And so once we've that, if you want to think about that as like a recipe, the preprocess is a recipe. It's saying, you know, take this and do this, take this and do this, return the total thing. Once we have that, we then take those essentially settings. We take the fit transform method, which again sort of takes those settings, applies that to your data, transforms it, and returns the associated thing and our original data. And then we return our fully transformed data set. So if you're looking at the steps, that's kind of exactly what's happening here. Now, if that looks kind of familiar to you, it should, because hey, that looks an awful lot awful lot like a pipeline, because that's exactly what it is. You and I on this humble little discussion section have just created our first pipeline. We have essentially taken all of these various data pre-processing steps, and we have merged them into sort of a nice single uniform process that we can then call, that whenever we get new data, we can just feed it into this method and return a fully processed data that we can then sort of feed into our learning model. And so essentially, sort of taking a step back and understanding what pipelining is and how it fits into the process, I mentioned up front that data science was really doing sort of a series of trials and errors. And you're going to play around with different things, and hopefully both in lecture and in these sort of exercises, you're beginning to see the various different things that you can do to your data, and the various different options that you can do in terms of which features you include, which you drop, which you augment, which you, how you impute, how you, like all of those things. You do those trials and errors, you try to get a result that kind of works. Once you've gotten that result, and again, you validated it, you want to ultimately kind of migrate your model into sort of a production environment. So, using the example from project 1 of Airbnb, where you want to predict a listing price. Well, your end case, let's say you get hired by Airbnb. Airbnb may say, well, whenever somebody signs up for an account, we want them to fill in information about their listing. And then we want to be able to recommend a rental rate for them based on the inputs that they've given us. And so essentially that's the model that you want to sort of move into production. And to do that, that's essentially where the pipelining is. So in the future, whenever any new input data comes in, you just kind of feed that in, you apply that to your model, and then you're good to go. So going back to that sort of monstrosity of a thing there, and we'll kind of try to walk through a little bit if you have sort of any additional questions, but to understand kind of all the steps that you're doing for your pipeline, essentially it breaks it down into the full things. So this is the high level thing. This is your output data. And to do that, you sort of call, again, your full pipeline, which like we said is your recipe. You run the fit transform and you do it on your raw data. Your full pipeline is you're calling this column transformer method that, again, you're importing, and you're dividing it into two things. You have your numeric and your categoricals. And so for your numeric features, you again have your recipe and you have your features. For the categoricals, we don't really have a recipe. All we're doing is one-hot encoding them. So we just have the one-hot encoding method and the features associated with that. And then you've already defined here, so for categorical features, you've already defined that in your data set is that. For your numeric features, it's a list here, and we can kind of go and look at this thing, but essentially previously you have, you've sort of cut ocean proximity from your numeric data. And so you have you just list those out. And then for your numeric pipeline, so that's this recipe here, we have your various steps here. So we've defined your imputer strategy. So for any imputed data, in this case, we're going to take the median. We have the augment features, and that's that function that sort of augments those features. And then we just scale all of our numeric data. So at a very high level, kind of going back to where is our one code here. So that, let me see if I can't make this a little bigger. That is essentially sort of how all of this begins to come together. And then if you look here, this class level function, again, is just designed to sort of run a script that then sort of creates and augments these features. We'd sort of define a few of our variables up front. In this case, again, like we said, housing numerical is our label, but we've dropped our categorical. And then we've imputed sort of a number of Python libraries to make this work. But that, in short, is really all we're doing with this big step here, and really all you're looking to do in terms of sort of recreating that for your own pipeline. Okay. So let me pause there and see how you guys are feeling with that.
So in the custom class you defined, augment features, you're assuming that X is a NumPy array, but when you pass your input values, you pass a pandas data frame into the pipeline. So what are the requirements for something you have to pass in to the data frame? Or sorry, to the pipeline?
Yeah, so good question. And one thing to note is that generally speaking, the output of your, so I'm glad that you kind of call that out. And I don't know that I can sort of give you the full answer to that, but you are correct in noting that generally speaking, sort of these work by taking sort of NumPy arrays and generally speaking, these start out as pandas data frames. And the reason that's sort of notable, for instance, is after you output this, it outputs as a NumPy array, but as you can see, the nice little data frame with, with their header labels and everything like that, those are sort of gone. And so, but I in terms of like the specific input and output requirements, I do think it needs to be in that sort of, it needs to be right, because if you look at this, right, the way in which we sort of feature these. So for instance, the way in which I'm sort of calling out my categorical features, I'm just saying it's ocean proximity. Well, that has to be a pandas data frame. I can't, if it's an array, I can't sort of call out my column attributes like that. This, because, so you'll see here within this expression, we have to sort of call relative column value. And that's what you're seeing sort of here, where you're associating column attributes and plugging those in, because Kyle, as you noted, what's being sort of inserted there ultimately is a NumPy array. And so you're sort of referencing array values. You can't just sort of leverage columns anymore. So I don't know if that's answering the question. Hopefully it's at least clarifying it a little bit.
So just in general, it's you input the pandas data frame and then everything else uses it as a NumPy array?
Yes, I believe that's the case. Yes. Yeah, and
Okay.
as a result, what outputs is going to be a NumPy array. Yeah, and by the way, you can feed a lot of most learning models, particularly if you're learning the scikit-learn model, can take either arrays or data frames as inputs to their thing. Oftentimes, they're pretty versatile in terms of taking their data inputs. Okay. So yeah, any other sort of pipeline? Okay, can you explain why you drop all the categorical features and then want to encode them? Okay, so let's see here. So you're, oh, okay. So yeah, so I can explain that. So you're not technically dropping it from your entire data frame. What you're doing in this example is, so what he's doing here is he's creating the housing numeric features thing. Because if you'll remember here, we have our pipeline here. Remember this little recipe here. So we're saying this is our recipe, our numeric pipeline, and we run it on our numeric features. Our numeric features is the list of the housing numeric. So essentially what you're telling it to do is run the numeric pipeline on your set of numerics and then run the categorical pipeline on your set of categoricals. So that's what's being done up here. We're just defining the set of numeric features that we're going to run the numeric pipeline on. So again, it's sort of, there's a lot here, but again, just kind of working, I always use like the peeling the onion metaphor. If this is the data that you're going to output, this is your pipeline data, you're going to run your full pipeline, which is again, your sort of your recipe. You're going to call the fit transform function, which essentially applies the pipeline. You're going to do it on your raw data. And then your recipe is a breakdown. You're again calling that column transformer, which transforms the individual columns. And again, that's a method you import. And you're going to run it on your numeric. You're going to run it on your categoricals. And for each of those, same framework, you define your pipeline, you define the recipe, and then you define which features in your data frame you're going to apply that recipe to. And that's essentially all that we're doing here with this. So, and hopefully hopefully that's feeling a little bit less ridiculous, crazy. Hopefully it's feeling a little bit more intuitive. And again, for project one, we're not asking you to sort of rebuild this from scratch. Essentially, we're just asking you to kind of take this existing code and manipulate it as you see fit to sort of finish your own project. Okay, so any other questions on that? Okay, cool. Okay, so then continuing our little journey there. So now that we've pipelined our data, we have our pipelining done. Now we're going to get into the splitting our data set and ultimately training our data set. And that's kind of what I want to sort of look at with you guys a little bit. So the first thing, so remember we talked about this last time already. I know we talked about it in lecture. Is everybody clear on why we do a train test split? Is everybody sort of clear on that concept, what we're trying to do, what we're trying to accomplish, and so on and so forth? Like, is anybody not really clear on what's happening with that? Okay, so everybody's good on that. Cool. Okay, so I mentioned this last time. There are a number of ways of doing your train test split. And for project one, we're just going to do kind of the very basic bare bones one. And that's sort of a random, essentially a randomized splitting of it. And also really, really easy for us to kind of pull this. But essentially the way you call them, once you've imported the library, the way in which you sort of do that, you define these four data, sort of these four arrays up front. Your training features, your testing features, your training labels, and your testing labels. And they're generated in that order. And then you just sort of call your train test split. This is the data that your data frame that you're going to do. Y is your associated labels for it. And then your associated test size, which is 0.2. Now, there's also another thing that's not in that thing that I do want to kind of call out for you all, which is random state equals 0. Out of curiosity, does anybody know what a random state is and how it's useful in terms of Python? Okay, good. Yeah. Okay. So Daniel says the seat. Dan, do you want to elaborate on that, or should I?
Sure. So basically, if you want someone else to, I guess, like replicate what you're doing, if you set a random state to like a number, then any kind of like anything that they write will also, you'll like also get the same output as anyone else who has the same random state or something like that.
Mm-hmm. That's exactly right. So I told you up front that train test split is sort of a random. It's true, man. It's my evil plot just to eat lunch. I was dumb enough to take a noon discussion. So because train test split is a randomizer in terms of how it splits, if you don't do if you don't seed it, essentially what you're seeding is you're saying, okay, I want this to run randomly, but once it's run randomly, I want to consistently reproduce that initial random splitting. And Daniel gave a great example of why that's important. If I share my code with somebody else, I want them to get the exact results. Or concurrently, if I rerun my Jupyter notebook, I want to make sure that this works properly. Or consistently, because if I don't have that random seed and then I just rerun the exact same blocks, I may get a completely different set of metrics because my training and my testing data will be different. And so exactly right. So having a random state in your code is really important because it essentially it makes it consistent. It sort of locks in your seed, if you will, for it, and says every time I run it, even though it's sort of random, even though it's arbitrary in terms of how it's generated, it will be consistent from there on out. So yes, so that's incredibly important to do. And then of course, the test size is important because that tells the splitter sort of how large to make your training, your testing in terms of cohort. So this just defines and says, okay, it's going to be an 80-20 split. And then one thing that you can kind of run with this, that just as a validation, you don't have to do this, but this is always kind of a useful thing, is I do you can call a shape method on it, which tells you the dimensionality of the associated arrays, and then it'll kind of give you a sanity check to say, okay, is this correct? And so in this case, what we're seeing here is so for our training data, we have it's a 353 rows by 10 columns, and our labels are 353. So that's perfect, right? That says for every row we have an associated label. And then same thing with our testing. So we can see here the number of labels for our testing data is equivalent to our rows, and our testing data has the same dimensionality as our training data. So at least eyeballing that, like, that looks correct. So we've done that correctly. Now we can fit that into our model. And then again, the code to actually kind of do this is really, really simple. You just import the model that you wanna run. And then you sort of define the model that's associated. You call that method. You then do the fit function, which is essentially the active training step. And you do it with your training data. So you're training your training labels. And then once you have that, there's a number of things you do, but like you can call the predict method to say, once you have that trained label, you can then use the X test to sort of generate a set of predictions. And that's what we effectively are running here. Then the final thing, I don't think I have explicit sides on this. I have just some kind of talking points on that, but we'll get to that in a moment. Is then your metrics. So, number of ways of sort of calculating that, but here, the way in which we're sort of generating our thing, we're doing this manually. You can oftentimes generate this some other ways, but we generate our set of predicted labels using the model that we've trained. We call the predict thing on our test thing. We then do a mean squared error, which call again, we import our metrics libraries. We then just call the mean squared error method. We do our predicted ones versus our actual labels that will return the errors. Then we just sort of use that to calculate our RMSE, and we return that. And by the way, for project one, that's all you have to do, and then you're done. So in terms of, before we kind of, I want to talk a little bit about, I know we've sort of talked about in lecture, I do want to talk a little bit about like metrics and what it means and how to interpret it and the importance of that. But like in terms of actually getting project one done, do you guys feel like you're equipped to do so? Do you feel like you kind of understand all the steps that you're being asked to take and the code that's associated with it? Or is there any point where you guys are feeling lost? And I'm going to strategically eat more lunch and see if anyone has any questions. You guys being so like cooperative and helpful and not asking questions is really awful for me if I'm trying to eat lunch.
Oh, I have a
Okay.
question. For the Airbnb data,
Mm-hmm.
there's like the augment features class. Did we still need to do that? Because I think we did that for like a step before that. It's like it just asks you to add 3 features of your choice. Is that
Yeah.
like not something that's augmenting it?
So are you asking, does the augmentation step have to be in your pipeline?
Yeah, because there's like the whole class for that, and it's like, I guess basically doing the same thing as the previous step, or
It
previous?
is, but I think so we are kind of also asking you to impute your missing features. So
Yeah.
yeah, so in both of these, we're sort of asking you to do it explicitly. And then effectively what we're asking you to do is just to kind of create the pipeline. So we are kind of asking you to essentially redo that work. But the idea is, one, we want you to do it explicitly and kind of explore that. And then two is just kind of wrap it up into a pipeline step. And so that's really more of what that step is asking you to do, even though you've technically done it already.
Oh, okay, so it's just like repetitive, but like it's just so you put in the pipeline, I guess.
Exactly. And again, that's that whole idea, going back to the slides, where it was like a moving from like experimental to production. So pipelining is that production step. Pipelining is when you've already sort of figured out your approach and you just want to streamline it. So that's effectively what you're doing. So you can view like the steps up here as your like experimental step. You're testing different augmentation strategies. You're plugging those different data frames into your learning models. You're seeing kind of what works and what doesn't work, and you're trying to like output it.
Okay.
Yeah. So, but yeah, really, really good question.
Thank you.
So for the prepare the data section, are we creating a single function then, or is it like we're just doing these individually, just not as a function? Because it seems like you're supposed to implement it like piecewise, whereas in the actual like example, they just had a single function do all of these things together.
Yeah. Okay. So good question. So it does actually kind of replicate this. So even in our example, we do have the dealing with incomplete data as a discrete step, and then we do have a augment data. I think we have that as a discrete step as well. So we're kind of mirroring that. So you are going to be asked to do augmentation as a discrete step, and then we're going to ask you to do the imputation as a discrete step. And again, just follow the example code here. We're not looking for you to kind of reinvent the wheel with this. Just, we want you to just be able to take the existing code, apply it there. Then we're going to ask you to pipeline it. And then that's where we're essentially, yes, we're going to ask you to kind of redo that augmentation, that imputation, but this time sort of wrap it into that single kind of pipeline thing. And that's where that sort of pipeline thing is, where we want you to have sort of your full pipeline, which is comprised of your numeric and categoricals, and, and for your numeric, presumably you're going to sort of do an augmentation as part of that. And that's where you're going to call this. So
okay, that makes sense. So basically it's a little repetitive at the end then.
It is,
like,
yes, exactly right. Yes. Yeah.
Okay.
And again, the whole idea there is it's supposed to be repetitive because your pipeline is supposed to be once you have sort of figured out your method, your pipeline just consolidates it. So exactly right.
Got it. That makes sense. Thanks.
Yeah, absolutely. And again, remember, can't emphasize this enough. This is the bake your first cake project. We're not looking at, we're not looking at the performance of your model. We're not looking at evaluating the metrics. We're not looking at, whether or not the features that you augment are useful or meaningful. All we're looking to see is you go through the motions. So yeah, and so again, this is kind of one of those things. I know we've talked a bit about all these different metrics in class. We've talked about mean square, root mean square, mean average error, R squared, different things, and it's talking again about like the different approaches and necessarily right and wrong. The different kind of ways of keeping score really sort of depend on the specifics of your model. And part of your job as a data scientist, when you're given a problem, when you're given sort of a thing, is to determine the scorecard, is to determine how you're going to evaluate your model, what approach is going to give you the best results. And we talked about like how you penalize different types of errors. Well, that's going to depend very heavily on your goals for the model. And there isn't always a right or a wrong answer to that. That's part of your job, is to kind of make that decision. And then, and again, and then there's sort of a good question, like the results, are these any good? Like, so we got when we ran our property thing, I think we got an RMSE of 67,000. Well, that does not sound particularly good for a model if you were looking for trying to predict property. So I would probably say, objectively speaking, that's not a particularly impressive model, all things considered. But again, it's not kind of obvious always what sort of a good and acceptable parameter will be. And again, part of your job as a data scientist and working with clients and sponsors and everything like that is to understand, what an acceptable error bound is going to be. What are you sort of willing to accept in terms of errors? So, and yeah, so I think, okay, so I think that's pretty much the material that I wanted to cover today. So I for the rest of the thing, I do want to kind of open it up to any additional questions. And then my goal is, we'll talk a little bit about announcements. And then my goal is, I want to try this with you guys, is to kind of end the session again with a breakout session. And so the idea here is going to be, I'll break you down into smaller groups. Whoever wants to drop can feel free to drop at that point. Not really covering any new material. And it'll be a chance both for you guys to maybe like start working on the homework, start having some questions, but also just give you guys a sort of an unscripted, unfiltered chance to kind of meet and interact with one another. Oh, speaking of, hi. If you haven't joined the student directory, or if you haven't joined the Secret Broom program, I would highly encourage you guys to do so. I think about a third of the class has joined the directory already, which is awesome. I'm really, really thrilled by the participation. We've also had a very robust, not quite as high, but very robust participation in Secret Broom too. And I would just encourage as many of you guys who are up for it to do it. Also, I would say, if you have submitted to the directory, one of the blessings and the curses of it being popular now is it becomes much, much harder for any individual row to kind of stick out. So if you have joined, I would highly encourage you to take the initiative to message someone else as well. Don't just kind of sit there and wait for someone else to join you. Message you, because yeah, thankfully a lot of you guys have filled it out. So, a little harder to kind of stand out. And I will note too, it's kind of one of those funny things, like when you start school, right, there's like freshman orientation, and there's like that weird sort of social bubble for like a week or so, where like it's perfectly okay to go up to complete strangers and be like, hey, who are you? Where are you living? What's your major? Right. And then like there was like that bubble, and then that kind of goes away really quickly. And then at some point it becomes kind of weird to do that. So hopefully, having that directory, saying you're out there, you're open to meeting people, it says like, yeah, it's totally cool to like message and try to meet people. And, hopefully you're kind of like in that freshman orientation bubble where it's totally okay to be like, hey, I saw you on the directory. Like, I really liked what you said about X. It'd be cool to do whatever. Out of curiosity, has anybody actually messaged or taken advantage of the directory? Okay, I'm seeing at least one yes, which is awesome. Thank you, Jacqueline. Oh, yeah, scrolling up, I'm eating dumplings for what it's worth. And then, yeah, so there was a question about, you expected to get an MSc within a certain range? So no, you're not. Again, you will not be evaluated at all on the performance of your model. Your model could be atrocious. It doesn't matter. At this point, we just want to see you go through the motion of getting a model, getting the metrics associated with it. That's all we want right now. Future projects, your performance is going to start to matter. But for right now, we just want you to go through the motions. Oh, and then some quick announcements. I don't know if you all know, but it is a holiday Monday, so you all have a long weekend. I hope you take advantage of it. Do make the effort to get your project one done, as it is due Thursday, and at least get started on homework one. I also want to kind of throw this out next. So this week we did a contest. I want to do a theme, and next week's theme is going to be a pajama party. So if you've got that like awesome onesie that you've been waiting to like rock, now is the time to do it. Next week is your time to shine. Okay, pajama party is happening. Yeah, I know. Basically, everybody is showing up to these things in pajamas, but like now you have an officially socially sanctioned reason to do it. So, oh, and then before we break out into sections, we have very, very important. We have to announce the winners.
Yeah, so it was a pretty close tie between Josh Lee and Jody Lynn. However, Josh Lee got one more vote, so he'll be the winner this week.
Let's go. Thank you.
Josh,
Thank you.
and you were the obviously you were Bahrain.
Yeah, you can't beat her. She's too
Well
good.
done, man. Okay, DM me your email. You have a prize waiting for you.
Sweet. Thank you.
Well done. Okay, so before I break down to the breakout groups, anybody got any specific questions for the good of the order? Okay. So,
I kind of have a question about logistics. There's
me.
still some people on the wait list. I was wondering if you guys talked about that like at all, because I tried to reach out to the professor, but she hasn't emailed me back, and I also posted on Piazza. But yeah, just wondering if there's any chance you guys are going to approve anybody from the wait list, because she didn't mention anything in lecture.
Yes, I don't have any insights on that, but I can try to ask the professor about that. I mean, my hope is we'll get as many people in as possible.
That would be awesome. Yeah, because there's just like a few people left, and I was just wondering because I think today is like the last day to add people from the wait list. Otherwise,
okay.
it's gonna be dropped.
Okay.
So I don't know if she's aware of that, but yeah, just wondering.
I'll ping her right after I'll tell you what, I'll ping you right after I break whoever's left into our little breakout groups.
That'd be awesome.
Yeah,
Thank
and
you
by
very
the way,
much.
I should mention I'll be sticking around. I'll be jumping from group to group. So and again, my goal is to kind of get you guys started on the homeworks and stuff. So talking through that. So for what it's worth. But I will say but I will message the professor as well about the wait list, because you guys do need some stuff. Okay, one other thing I like to do with these groups is, you probably already saw that, icebreaker. So one of the things I kind of want to hear, and if you guys are kind of talking around yourselves, unquestionably COVID and this whole lockdown quarantine has just completely upended pretty much everyone's life drastically. And there's this light at the end of the tunnel. Vaccines are rolling out. They're talking about reopening. UCLA is going to be open in the fall, right? Like it's still really bad, but maybe it's going to get better in the not too distant future. So one thing I'd love to hear is kind of how you feel you've changed by this process. And when things are quote unquote back to normal, what are you going to take from this experience? How are you going to be sort of different as a result of it? Hopefully for the better, but maybe also not. So I do kind of, as something maybe to talk about in your groups, maybe we can sort of talk about that too. So I'm going to stop the recording. I'm going to break you all into groups, and then and I'll be kind of just hopping around for the next half hour or so, just going over stuff.